Good afternoon, one and all. Welcome back for the session 6 on sustainable solutions in hybrid vehicles, a 5-day faculty development program organized by Mangalore Institute of Technology and Engineering, which is sponsored by AICT. Today's session, that is session number 6, is of the topic thermal management in electrical vehicles by Mr. Ravi Ranjan, Mahindra Research Valley Center. So I will be glad and happy to introduce Ravi Ranjan to all the participants here. Mr. Ravi Ranjan is working as a lead engineer in Mahindra Research Valley, has received his BTech degree in mechanical engineering and MTech from IIT Madras. His work resulted in the development of robust thermal systems for KUV, TUV, and XUV platforms. He has over 10 years of research and product development experience. His research areas include thermal management of electrical vehicles, modeling and analysis of thermal systems, product design. So he received more than 9 Best Performing Award and 1 patent award for his contribution in the areas of new product design and development. Presently, he is responsible for developing the cooling system for IC and EV powertrains and developing various methodologies on vehicle energy management for the improved fuel economy and customer delight. He also holds 3 SAE publications. So, with this brief introduction, I would now welcome Ravi Ranjan sir, and I would now request Ravi Ranjan sir to take over the session, sir. Over to you, sir.
Good afternoon, all of you. Am I audible?
Yes, sir, you're perfectly audible, sir.
So just now I have shared my screen. So whether it is visible to all of you.
Yes, sir. Yes, sir. It is visible.
Post lunch session is always considered as a tough session to sit and attend a lecture. I will try to make it as much as possible interactive and interesting session to all of you. So today I will present a thermal management session in electric vehicle. So all of you know that nowadays there is a craze of electric vehicles all over the world, and in Indian market also there is a lot of penetration of electric vehicles. Considering this CO2 requirement and your CO2 pollution norms. So, so we will focus here the requirement of thermal management electric vehicle. So why there is a need of thermal management electric vehicle? Although for if you see this IC engine, we have cooling system, and that is perfectly fine. But once we come to the electric vehicle, so what a special is there? So that we have to be more cautious about that. So we will see how things are going changed when a vehicle system is moving from IC engine to electric vehicle. So if you see this electric vehicle, so electric vehicle basically we have different operating thermal boundary conditions. So you must be knowing the architecture of electric vehicle, which is having the electric motor, powertrain, controllers to control that one. Apart from that one, you have the battery pack also, which is your fuel system. So in IC engine, you have the fuel system as a gasoline or diesel, but you are not providing any cooling for that one. But in case of electric vehicle, you have to provide the cooling of the battery pack, because this is the requirement of the battery to maintain the performance as well as the life cycle. So if you see my right hand screen, so the controller requires the temperature that it has to be within 65 degrees of temperature boundary limit. If you do the motor part, electric motor, which we are now using permanent magnet synchronous motor, that is close to 85 degrees Celsius. Now, if you're coming to the battery pack, so I have limitation that whatever be the climatic condition, like from minus 30 to 50 degrees Celsius, we have to maintain 15 to 35 degrees Celsius of the battery pack. Then only it will perform and provide the desired life cycle. So, so here we are able to understand that we have to provide the thermal management electric vehicle. Second thing, we have various design challenge because three circuits are there and 3 temperature loops are there. So it looks like a complex. It is going to be a complex circuit because three different cooling architecture will be there. Three different temperature management will be there. Second, other requirements is like suppose you are going in cold environment condition. So motor will reject heat. At the time you will be needed the battery heating requirement. So can you are going to utilize the heat? That is another challenge for it for a designer. Second thing, if you consider electric vehicle, so you have the opportunity to only to provide only one compressor and only one condenser system. We call it a HVAC unit. So the same HVAC unit is cooling your passenger, which is a very much important parameter for the vehicle system to sell. And second thing, the same system has to support your battery pack. So whom you prioritize during a vehicle running condition, because the system is same. Second thing, whether the system which you have designed is robust enough to handle both the cooling requirement. Another question will come, how you are managing the extreme temperatures. Like if you went to Leh Ladakh, where you have the -5 to -10 degrees Celsius temperature. So how you are going to manage this one? And now once you come to the Rajasthan area, so there you have 45 degrees of Celsius. So how you are going to manage it? Now you come to the southern part where you have extreme humidity area. So again your HVAC system will be loaded. So these are the different parameters are there, and the same vehicle system has to satisfy all the conditions. So this becomes a challenge. Now the question is, okay, we have to do the thermal management, we have to do the cooling system. So what a big deal. We can do it, right? But the problem is that in case of electric vehicle, all the power, which is known as the auxiliary system power, is coming from the battery pack only. Either you are using it for the traction requirement, or either you are using for the cooling requirement, for the passenger cooling as well as battery cooling, or your controller's cooling. All power has to come from the battery pack. And the biggest advantage or the challenge, I can say, you cannot refill your battery pack within 5 minutes as you do in IC engine case. So it is require 4 to 5 hours of time, right? If you are going for fast charging, then minimum 1 hour the requirement. So our main intention is that my system should be designed in such a way that it should not deplete my battery power too much to support the functioning of the battery pack as well as the other uh, accessories, cooling accessories for the powertrain and the controller, because power is coming from there and it will deplete your range. So this is one of the fundamental requirement. Second requirement is the external environment, like bumper to bumper traffic, small opening area for the electric vehicles, climatic variation, aggressive acceleration. So these all parameters is nothing but directly impacting your thermal duty cycle. So again, thermal duty cycle more means more power from the battery pack. More power from the battery pack means you have to invest more power in the auxiliary system, and little power, and like there will be become ratio like 70% going to the traction, 30% going to the auxiliary system. So ultimately your range will reduce. So, so if you see the idle system of electric vehicle, idle system says that I should not invest any energy apart from the traction. But because of this limitation, we have to design our system intelligently. So that is the reason this thermal management of electric vehicle becomes a challenge. And also it becomes interesting that how engineer is going to deal with that one. Now, if you see this battery cell performance, so if you see the from the thermal perspective, so from the last slide, I have also told, like we have the desired range from 15 to 35 degrees Celsius only. So with this range only, I am able to operate the battery pack. When I'm going to operate the higher range, higher, so see, the deterioration will happen and the energy will deplete fast, and also life of the battery pack will come down. When you are operating the lower temperature, that is also a sluggish electrochemistry. That means discharge power will come down. Now you are not able to charge your battery pack. So these all are my red zone. I don't want to operate in this case. Okay, and this is only the desired zone. And our Indian climatic condition varies from -5 to 50 degrees Celsius. Okay, so that is the reason we need a proper thermal management for the battery system. So we will, in the coming slide, we will come to know how we are maintaining this particular band, by optimizing the thermal architecture, or do we have the different options of thermal architecture to satisfy this requirement? Now coming to the next part, we have to understand the heat flow diagram. So this is a general heat flow diagram. So any component, let's suppose you have a controller, okay, or you have a motor. So this controller and motor is your heat source component, from where your heat has to come out. So this heat has to come out from the two ways. Either you can directly go for heat convection through air, or you can provide some cooling mechanism, some water mechanism, cooling system, water fluid mechanism, so that the coolant will take out the heat from the system, and it will make the component in a desired range, desired temperature range. So this is the basic heat flow diagram will follow for all the components of electric vehicle. Now come to the heat sink components. So let's suppose if you are going with the cooling system for liquid cool system. So for liquid cool system, heat energy will be carried away from the heat source component through coolant, and the same coolant will have to reject the heat through the means of heat exchangers. So we will discuss how many types of heat exchangers typically applicable for the automotive field. We will not go all types, but only we will discuss the typical. And since this is a closed loop system, so how we are maintaining the closed loop system apart from this heat sink and heat source, whether there are other components also, so we will discuss in the coming slide. Now we will go to the electric vehicle layout. So this layout I will show only from the thermal point of view. It will not having the relation like how motor and other controllers are connected. If you see this electric vehicle layout here, so this front part is nothing but your power pack unit. So power plant unit. So in the power plant unit, you have you can consider IC engine is replaced by your motor and controllers. So here you are able to see that there is a traction control unit, motor, DC-DC, OBC, LTR. So these all circuits, this is a thermal circuit which constitutes of uh, powertrain side, and there is a fuel system on the right side. So this fuel system is consists of your battery pack, and apart from the battery pack, since we have to maintain the desired temperature range, so we have the other accessories like heater or chiller. So uh, you so here we will discuss about DC-DC converter, OBC charger, low temperature radiator, water pump, cooling fan, e-motor. So these are my heat source. Okay, and these low temperature radiator and water pump and cooling fan, these are like heat sink. Will help me to take the heat energy from the system and to maintain as a desired temperature after rejecting to the air system. Now coming to the battery pack, so we have this BMS chiller, water pump, and HVAC unit. So we will come to know like how this battery pack is connected with the heater and the chiller. So what is the role of chiller and what is the role of heater to maintain the desired battery pack temperature? Since we have considered that, we will come to know the components, like what is the low temperature radiator components. So these components where we talked about in the heat flow diagram, that we have heat source and we have the heat sink. So we will come to know heat sinks type. If you see, one type is your plate heat exchanger. So where one side will be the hot fluid and one side will be the cold fluid, or we can say one side will be your refrigerant and second side will be your coolant. So that this kind of arrangement we are applying as a chiller. We call this as a chiller for the applicable for the battery pack. Second thing, for we discussed about LTR, so low temperature radiator, or simply you can say heat exchangers. So in automotive field, we call heat exchangers as a radiator or high temperature radiator or low temperature radiator. This is simply the classification. So this is the typical radiator which we are using for the automotive field. So this is a tube and fin type radiator, and they are usually cross flow types. So here you will have, you can see that we have this lower fin kind of thing, and inside this is the tubes where the coolant is flowing inside the tube, and here in perpendicular direction air flow is happening. So through cross connection, so this is your coolant flow and this is your air flow. So through cross, heat rejection is happening at the sink area. There are different types of radiators we deploy in automotive field. One is your downflow radiator, one is your cross-flow radiator. So this downflow and cross-flow radiator depends upon the packaging wise, because this has to be come in the front of the vehicle. So depending upon the packaging system requirement, we go for cross-flow and downflow. Now for EV application, we use a special type of fin and tube type, that is called U-flow type radiator. So what is happening in U-flow type radiator? Uh, we have coolant coming from this area. The whole coolant is traveling, and again it is coming out from this spout area. So you can see that 50% only utilizing for the one pass. One can say it's a dual pass radiator. So that is also somehow correct only. So this is done. So one can ask why especially we are using this U-flow type radiator, because as you've seen the requirement of the temperature. So requirement of the temperature is close to 85 degree and 65 degrees Celsius only, and you are deploying the system at the ambient of 50 degree. So 50 degree to 85 degree or 50 degree to 65 degree, the delta is very less. So if you are increasing the surface area, I'm talking from the fundamental thermodynamics point. If you are increasing the surface area, then you will be able to reject more heat. So within the same packaging area, if you make the surface area or flow area larger, so you will able to reject the more heat. So that is the reason for EV application we are providing this kind of typical U flow radiator. There are other heat exchangers also. We are using the heat pipes. So the best example of heat pipes is our laptops, chip cooling. So the reason is why we are using this heat pipes. So let's suppose you have a system here, and you have the cooling channels like this. So this is the cooling channels coming, and here you have one heat source here. You have only one heat source here, but you want to bring the heat from here to here. So there is one way that the cooling channel itself you can route it. So this is again a cost impact task, and also the pressure drop will increase because you are making a lot of bends. So what is the best way that you provide the heat tube? So what the heat tubes will do, it will transfer the heat from here to this area. So that is the reason we are using this heat pump, and also it is very much effective when you are going for this controllers or your chip cooling, MOSFET cooling. So once you go to the inverter part of the motor, which is providing in the vehicle system of the electric vehicle, so on the spot area you will have the heat zone. So and you have one coolant gallery at some different location. So with the help of this one, you will be able to optimize your system within the cost limit. How it works? So where this is the high temperature. So this is a simple copper tube filled with water system. Simple water will be there. So at one system where the heat is there, so it will evaporate, and from other part where the cooling channels are coming, so it will condense. So based on that, this latent heat transfer will happen, and accordingly, the high temperature will become low, will become gradually come down, and cooling will be achieved. Now we need to understand the support system, like to make the closed looping. So coolant has to flow from high temperature to low temperature, or from the source to the seat. So for that one, we are deploying this electric water pump. So it's a 12-volt electric water pump, which is delivering close to the requirement, like 10 lpm to 30 lpm. And since we are using this low temperature radiator, so we need the airflow, because from sink area we are only rejecting heat through the air only. It means the radiator is interacting with the air. So for that one, we have to deploy this electric fan. So these are the just the basic components you should know what is coming in the electric vehicle. Now, now we will understand this thermal control methodology. So what are the heat removal methods is there for the power electronics cooling as well as the battery pack cooling. So one method is air cooled. So the desired area, like one example is here in the left side is your piston rings and cylinder area of the motorcycle. So we are directly flowing air to cool this uh, to maintain the temperature of the system under control. This is one of the method where air cooled is directly deployed. So what we are doing, the system which we are cooling. Hello, hello, am I connected?
Yeah, yes, sir, Ravi Ranjan.
Yes, sir.
Yeah, yeah, yeah.
Please continue.
So, the desired area we are providing the fins, and the fins are getting air, and here natural or convection, forced convection coolings are happening. Second one is the liquid cool system, where we have high energy transfer, like IC engine, where combustion is happening, and around 20-30 kilowatts of radiation is happening. So air cooling will be not sufficient. So what we are deploying here, we are providing one external heat sink source filled with the coolant system. So coolant will take the heat from the here, and the finally coolant will reject the heat in the radiator system through the air method. These are the two basic methods. So now coming to the e-powertrain management. So how we are deploying these two methods, we will come to know. So one is your providing the air cooled through air. So if you see the two-wheelers or three-wheelers or four-wheelers, they don't have any liquid cooling system. So what they are providing at the controller part, they will paste this type of cooling fins on the controller. So I will just make you understand. So if you see this will be your vehicle diagram. So the cold air is coming inside the vehicle. So the cold air is coming inside the vehicle through the supported with the fan, and here your components are kept. So here, let's suppose here if you have traction control unit, or if you have DC. So what we are doing directly, we are pasting this kind of arrangements, fins. So whatever the air it is getting from there, so the air will interaction will happen here, and it will take away the heat from the TCU, and the desired temperature of the temperature control traction control unit will be maintained. But there is a limitation of this system. It is only possible to go with the system when the heat rejection requirement is less than 500 watt. If the heat rejection is more than 500 watt, then these methods are not applicable. So that's the reason. Two-wheeler we are using, three-wheeler we are using, and the four-wheeler we have limited, like more than 40 kilowatt powertrain, we are not going with the air cool system. The second is applicable for the EV motor cooling fins also. So this is the normal thing which any motor, if you see electric motor, so this kind of fins arrangement will be there. In the vehicle system, what we are doing, we are just putting one additional fan, so that forced convection will be always happening, and the temperature will be always kept within the check limit. And now heat removal by liquid. So if you see now I have the same component, DC I have, again E motor we have. So what we are doing, we are providing this cooling plates. So in cooling plates, if you are able to see the tubes, so these are the tubes. So here these cooling channels are provided, and on the tubes we are pasting this control module. So this module will be pasted. So this OBC module will sit here. This DC module will sit here. This ECU module will sit here. On the E motor, directly we will paste this kind of cooling plates, so that heat rejection will happen on the faster range. So this is applicable whenever heat rejection is more than 500 watt. Okay. So now we are providing the coolant to reject the heat. So other accessories will also come into picture. That is your low temperature radiator, water pump, and cooling fan. So that what we have discussed in the previous slide. So these all about from the electric powertrain, where we have the requirement of temperature boundary 65 degree to 85 degrees Celsius. So now considering the environmental condition, which is 50 degrees Celsius, so we are able to manage through air cooled medium or liquid cooled medium. Now coming to the battery pack thermal management. So in battery pack thermal management, we know that the temperature requirement was close to 15 to 35 degrees Celsius, and we are operating from minus 10 degrees to 50 degrees Celsius. So we have to go for some additional case of thermal management, either by providing heater in the low ambient condition, or providing the refrigerant cooling system for the high ambient condition. Then only we will be able to achieve the requirement of the boundary condition. So here I am presenting this two typical layouts. One is your left side is your air cooled system, where directly we are imposing air to the battery pack area so that cooling will happen, and right side will be the liquid cooling. So we will discuss one by one here. So if you see this battery pack, so what we are doing directly here, so battery pack AC directly supplied with the air. Okay, so one battery pack will be there, one big box will be there. Inside your plates are kept, and what we will do here, here we will put one blower fan, so it will suck the air from here, and exhaust air will go out. So this is the passive cooling, or we can say outside air ventilation. So this is applicable for nowadays. We are putting this kind of system for e-rickshaw and for the two wheelers. This is very famous in that one, and it's a very cheap, because only we are providing this uh, uh, exhaust system. Nothing else we are providing. But the limitation is what kind of. It also depends what the bond. It also depends on thermal layout. What kind of battery pack you are using, or what kind of battery chemistry you are using. If you are using lithium ion, then the requirement is different. You are using this lithium iron phosphate, then the requirement is different. So depending upon the battery chemistry, there is a temperature need. So accordingly, you have to select these baskets, whether to go with the passive cooling, or whether to go with the passive liquid cooling, or active moderate cooling, or active cooling entity. Now, there are certain vehicles in which battery pack. So what we are using it, they are using cabin air, passenger cabin air. So as you know, the human comfort is close to 25 to 26 degrees Celsius. So it means at all the condition, my air temperature inside the cabin is below 30 degrees. So here they are using directly, they are sucking the cabin air to the battery pack to meet the cooling requirement. Now, again, but there is a limitation for this too. For this one, we can only provide the cooling, but we cannot provide the heating. So now what they have done, okay. So what we will do, we will provide this air heater. So during your passenger cooling, so that air will go to the battery pack, and it will satisfy the hot ambient condition by cooling with the hot air. Now when we are going to the cold zone, so anyway, uh, heater will be switched on inside the battery, inside the vehicle cabin, so that the heated air will be deployed to the battery pack. So in that way, we are maintaining the boundary condition of 15 to 35 degrees Celsius. But since this is a air cooling system, so again, heat transfer in air cooling is much lower than the liquid cooled, as we have understood that 500 watt is the only limitation. So if you are going for the high powered vehicle or high voltage system, so this will be not applicable. But if you are going for the low powered vehicle like 5 kilowatt, 10 kilowatt, then you can go with this one. Now again, for the liquid cooling also, same thing, only instead of air supplying at the surface of the battery pack, we are providing liquid at the surface of the battery pack with the help of cooling plate, or maybe submerged cooling also. I think this is all are the same thing. Uh, Here also, instead of providing the air, we are providing a separate cooling loop. So that's the reason you are able to see the pump has came into picture, while here exhaust fan was into the picture. And here in the last part, where we are providing this refrigerant cooling for the hot ambient condition, and your heat, and your vehicle engine cooling, or you can say when the vehicle engine cooling is not there, this coolant will be there when you are going with the hybrid electric vehicle. So where you have one IC engine, so from there you are tapping the coolant, you are providing the energy to the battery pack. But in case of pure electric vehicle, you have provided one heater. So the heater will provide directly to get the desired temperature at the battery pack level. Okay, so I think this I have already explained. The passenger compartment evaporator we are taking it. So now what we are doing here in this one slight modification we have done. So whatever the refrigerant coming from the compressor, from the condenser, so we are dividing in two parts. One is going to the evaporator to satisfy the need of passenger comfort, and one is going to the battery evaporator. So we have given two evaporators, one for passenger and one for battery, to meet the desired need. So what will happen here? So some vehicles where the uh, uh, you know close to 40 kilowatt powertrain vehicle, where the too much heat is not there, but it is not able to meet the system with the passenger compartment air. So that time this will be very much useful, because here the amount of air which we are getting at the passenger compartment is close to 5 to 10 degrees Celsius. The same we are getting also here, 5 to 10 degrees Celsius. But in earlier case, 5 to 10, again passenger heating will happen and this air will become 30 degrees. So earlier we are deploying 30, now we are deploying 5 to 10 degrees Celsius. So we are able to meet the requirement by doing the certain changes. Second thing, for going for the higher vehicle power and also the battery chemistry, so that the requirement become more strict, like you always have to maintain 15 to 30 degrees Celsius. So definitely here we have to go for liquid cooling system. So in liquid cooling system, what we are doing earlier, in previous case we have deployed two evaporator. So here one evaporator will be there. We are also making one circuit, but this will be a special heat exchanger. This is nothing but your chiller. In the first slide, we have discussed about plate tube structure. So it is the same thing, plate tube structure, where you are taking one loop and making your battery system cool to a desired level. Also, for limit lower boundary is 15 degree. So in case of minus 10 degree of application or minus 5 degree of application or 0 to 15 degree of application, you have to provide the heating. External heating you are providing, and you are making the system to meet its boundary condition. Then only it will do the required performance. That's what we have understood when we have discussed this battery performance requirement. Now I will discuss this. This is the advanced EV thermal management, and right now this is what we are using in most of the vehicle application, and other OEMs are also going with the similar kind of architecture. So it's a three coolant loop mode. So we will understand what is this three coolant loop mode. Uh, if you see, we have this real world vehicle application, because a vehicle which is manufactured in Chennai, it doesn't mean that it is only made for Chennai. It has to meet the cold climatic requirement also. And the same vehicle is exported in the other European market, where the temperature is quite low, it can go minus 20 or minus 30 degrees Celsius. So our design should be such a way that it can cover all the uh, boundary speed of real world operating condition. So if you see the real world operating condition, so we have the boundary from minus 30 to 50 degrees Celsius. So this is our design criteria. So this is vehicle application, and we have desired thermal boundary condition for the battery pack, which is nothing but your 15 to 35 degrees Celsius. So now our objective is clear. We are operating in this field, and we have to achieve this requirement. Okay. So here I have made certain boxes. So if you see that when a vehicle is operating from minus 30 to 0 degrees Celsius, that means I have to provide heating to the battery system. Then only it will come to this desired boundary condition. So for this range, we have heating. Now, we have also discussed that there are certain heat rejections coming from the powertrain. So can we reuse the heat? So that idea we are applying here. So what is happening here, from 0 to 20 degrees Celsius? So the heat rejection coming from the powertrain. So that heat we are utilizing to heat the battery pack, so that when we are operating from 0 to 20 degrees Celsius, the heat will be added from this rejection. Heat will be added to this battery pack, and so that we will meet the required. So here heating will happen from the waste energy, which is coming from the powertrain. Now coming to the high ambient condition, where we are operating more than 30 to 50 degrees Celsius. So at that time, we cannot utilize the heat from the waste heat. We cannot utilize, because we have to go for the cooling mode. So at that time, we are providing specific chiller mode. So there, your electric compressor is coming to picture, which is a quite power consuming device. It close to consume 2 to 3 kilowatt of energy during the chiller application mode. So it's a huge energy, and if we are able to save that one, so close to 20 to 30% range will be improved if we are not loading the chiller of the battery system. So so you have to understand here, this is the advanced loop where we are using it. So this left part, we can say this is a powertrain where your electric motor, OBC, and charger and your controllers are there. And the right part is the battery pack, where your battery pack is there, heater is there, and chiller is there. So earlier we have the separate one. We have discussed, we have understood the separate components. Now what we have done here, we have integrated the circuit to the valves mechanism. So based upon the requirement, I am triggering this circuit. Based upon the requirement, this circuit will be triggered, and based on the requirement, the complete whole circuit will be triggered. So which we will come to know. Cool condition is nothing but I am operating in 0 to 30 degrees Celsius. So what I will do, whatever the heat rejection coming from the OBC motor and your power pack, so the heat will go to the battery pack, so that the desired temperature of the battery pack will be met. So this is the most optimum, I can say, energy management, where I am not investing any extra energy to meet the desired performance. So this condition will always give you the maximum range benefit to the vehicle system. Now second is the hot condition, which is typical Indian scenario. So here we are operating 35 plus and within 50 degree. So there, of course, uh, the the powertrain which we have to meet 65 degrees Celsius requirement. So here 65 degrees is the requirement. Here 15 to 30 is the requirement, and we are operating at 50 degrees Celsius. So both the loop now will run separately. So here your fan will be operational to cool the to maintain the 65 degree, and here your chiller will be operational to make the battery pack at 50 to 35 degrees Celsius. This we can say this is this circuit is most power consuming, we can say, condition scenario for the vehicle when it is operating in high ambient condition. Now cold ambient condition is nothing but when you are operating at 0 and sub-zero temperature, means minus operating point. So for power electronics and motor, if you operate at minus 5 degree, minus 10 degree, there is no problem at all from this power electronic side. But only problem will come from the battery pack, because you will be not able to draw the power from the battery if your battery is less than 10 degree or 0 degree or below less than. So the limitation will come, and that limitation, if you are not providing a limitation, then your battery life will deteriorate, and 50% vehicle cost is coming to the battery pack only. So here for this case, we are providing external battery heater. So this battery heater, what it will do, it will heat the this circuit coolant and make the system a desired condition. Here I want to also highlight the operation of this valves. This valve is nothing but it is closing and switching on and switching off based upon the circuit isolation. So when only one circuit isolation is required, so then the valve will be closed. So there will be no flow from this side and there will be no flow from this side. So this area and this area will be blocked, so that only this area will be operational. The same is applicable for this loop also. So this area will be blocked and this area will be blocked. So vehicle will be only circulating this part and only circulating this part. While coming to this part, it will block only this portion and this portion, so that the circulation will happen on both the circuits. So that just here we are utilizing the waste energy in nutshell. Now we will go to this thermal modeling part. So how we are doing this thermal modeling of the vehicle system. So this is the basic heat transfer equations which we are using it. So in modeling, basically we are doing convection modeling. So convection modeling, one is for air cooled system, if it is a free convection or natural convection, and when we are going for this liquid cooling, we are going with the forced convection. So I will not go much in this one. It's a basic theory. Now, as an OEM or automotive sector, what we are using, that I will focus more here. So what we are doing here when we are going for this thermal modeling, so we are directly using empirical based correlation, because if you see this kind of equations, so it asks for certain assumptions like your PU structure will be like this, your boundary conditions will be like this. But in this case, whatever the pipes are there or whatever the components we are using, that has very irregular geometries. It is not a uniform thing, and properties are also not in isotropic in nature. So there is a limitation that we are not using those formulas, but that is the basic to start. So now once we are going for the thermal modeling, so let's suppose we are uh, going for this pipe flow where your heat rejection is happening in the coolant channel. This coolant channel is nothing but it's a pipe structure where the water coolant is flowing, and there at the surfaces the convection is happening. So these kind of correlations we are using it. So with this help of correlation, what we are getting, we are making our system fast, and it also become robust. Why I'm saying robust? Like when you are changing your dimension by 10% or 20%, so directly you can add the factor when you are using this correlation, while it is not applicable when you are using the exact equations which we have discussed here. There are other ways also, like if for certain geometries some correlations are developed, but for certain geometries correlations are not developed. So there is a way that we are considering in this form. So what we are doing here, we are performing test. So test will be steady state and transient state. So what we are doing here, we are using lab test. So lab test component will be tested with the help of with steady condition and transient condition. And in steady and transient condition, we are monitoring the temperature of the components. So let's suppose this is your component, DC-DC component. Okay, and here you want to monitor. Here you are providing one cooling system. So since you are part of the cooling system, you know the flow rate, at what velocity coolant is going. So V1, V2, you know the temperature of this component also. So based upon this measurements, you are basically coming to one empirical correlations. So that's what we are fitting in the simulation. So when you are going for this MATLAB simulation or any open forum simulation, so the application will be same, methodology will be same. There are certain analogy also we are using the scroll bar. So this single phase system, when you are dealing with this radiator system or ATR system. So in the radiator tube, if you see the radiator tubes, which is close to 1 and 2 millimeter height. So inside tubes there will be lot of dimples. Okay, so the flow will become very much transient. So normal equation will be not able to use it by through hand calculation. So there is one analogy called the Kolban analogy, where we are using this kind of equations to get the desired result. Again, here also you are using this test bed correlation, and there are certain correlations also developed by some of the authors, like one Saha correlations is also famous for your single phase, so that we are using it. So these all are for single phase system, where you are dealing with especially for the electric powertrain, where coolant will be only in the same form, or it will be only in the liquid form. Now coming to the two-phase fluid system, where you have the refrigerant system. So for refrigerant system, you have the choice whether you use the experimental result or you can use the empirical correlation. So there are certain empirical correlations which we are using, like Nusselt number correlation, when for the single phase. So if you see there for refrigerant side, there is a single phase also, condensation phase also, boiling also. The reason is that because in the same condenser, one side gas will enter, and in other side your liquid will come out. Okay, so here lot of phase transformation is happening in the same unit. So that's the reason all correlation has to be put it while doing the simulation through MATLAB or any other 1D simulation tool. So some of the name I have mentioned, you can check this one, how they are using it. but these all are well-defined correlations, and it is close to more 90% correlated uh, correlation choice, what we are observing in the industrial field. Now coming to the next part, we have considered the how we are doing the thermal management with the help of heat source definition, heat sink definition, boundary condition definition, different layout architecture. Now we have to understand how the heat rejection is happening at the source level. So how this DC-DC is generating the heat, or how this battery pack is generating the heat at the battery cell level. So if you see the battery performance parameter, so we always consider here ohmic losses. So what is happening here in the battery pack? So in the battery pack, there are certain internal resistances, which always depends upon the state of charge as well as the temperature. So at 40 degrees Celsius temperature, your ohmic losses will be different. At 20 degrees, it will be different. At 10 degrees, it will be different. And since we have the range of the battery temperature from 15 to 20, 35 degrees, so we have to consider all the points, so that the system will work as a lookup table. Like when your battery is running at 15 degree, it will take the resistance value of 15 degree and provide the required amount of losses to the system. Otherwise, what will happen if you only put one data value? Then the simulation and prediction will become wrong, especially for the battery pack. So another interesting thing with the battery pack is it has a resistance value for charge cycle different, for discharge cycle different. So for both the cycle, you have to consider uh, how the resistance is changing with respect to state of charge and temperature. SOC is you can consider uh, if 100% means fully charged, if 0% means fully discharged, and the battery pack, the battery cell which we are using, the lithium ion, the advantage is it always give flat delivery from 10 to 100% SOC. So most of the OEMs and automotive manufacturers, they always use SOC close to 90% only, or you can say depth of discharge, that is called DOD. It is 90%, from 100% to 90% only we are utilizing it. The reason is that because at that curve you have flat voltage delivery, so it will work like this. This is you have battery voltage, and this is your SOC, or DOD, whatever you say. It, it will like this. So from here to here, it has 3 volt. Once it is going, consider this one. So once you are going below 10%, only it is decreasing. So that's what we are only allowing to 10 to 100%. Okay. So the basic concept is we have to consider ohmic losses, and we have to always go for different charge and discharge cycle at different temperature, and distance value has to be considered. Directly we have to impose it to our simulation model. There is a choice of simulation model. You can go either for any commercial software or open forum softwares, or maybe your MATLAB. Now I will show the energy consumption modeling, how the modeling is happening at the vehicle level. So if you see the right side, we have this vehicle. So in vehicle, we have to put certain parameters, like what is the mass of the vehicle, what is the CD of the vehicle, and what is the rolling resistance of the vehicle. Because this is the only parameters which will give you the traction requirement when you are accelerating the vehicle, and deceleration requirement when you are going for the like traction deceleration energy requirement when you are decelerating the vehicle from high speed to low speed. Again, this is driver just to follow the drive cycle, and here we have motor, here the battery pack, here we have auxiliary system. So here I want to explain that here I'm showing one drive cycle where this is called MIDC, modified Indian drive cycle. It's a legal cycle. So you are able to see it replicates the basic city cycle where you have the velocity from 0 to 50 kmph, and in some point we are running 30 kmph also, and a lot of braking events are happening. So if you see here, these are the acceleration event and these are the braking event. These are the acceleration event, these are the braking event, and these are the constant speed. So typical this kind of cycle we face once we drive in the city cycle. And this is the battery consumption. So whenever we are accelerating the vehicle, so battery is coming, power is coming out from the battery. So that is the reason we have this. It is a negative loop. And when we are decelerating it from this to this, so electric vehicle is capable of regeneration. So we are taking advantage of regeneration. So energy, kinetic energy will transform from wheel to back to motor, and motor will now convert this kinetic energy to electrical energy, and the electric energy is put it back to the battery pack. So this is the kind of energy we are getting as a recuperation. Okay, so I can say the upper is recuperation energy, and this is the energy consumption. Okay, now either you are accelerating the vehicle or decelerating the vehicle, there is always change of current from the battery pack. It means there is always if current is drawn from the battery. So since internal resistance is present, so either you discharge the battery or either you charge the battery during the running condition. Heat will be always generated. Correct. So during consumption and during regeneration, both the time heat generation is happening at the battery pack level. The same heat generation is happening at the inverter level also, as well as the motor level also. There are certain ECUs which is loaded with the auxiliary system, so those are also loaded. So in fact, for the whole cycle operation, you have the heat generation. But in case of IC engine, when you are accelerating the vehicle, you have high heat generation. But when you are decelerating the vehicle, fuel consumption is less, so heat generation will be less, because there is a concept of cylinder deactivation. You are burning less fuel, so cooling system load will be little bit less when you are decelerating it. But in case of electric vehicle, it is not less, it is actually more when you are decelerating, because reason is in deceleration, whatever the energy is going to the kinetic energy, you want to recuperate all the amount of energy to your system. Correct. So let's suppose in acceleration phase, if you have consumed 50 units of energy, during deceleration, you want to accept all kind of kinetic energy available during the deceleration. So here availability of energy will be more than the 50 units. So accordingly, the heat regeneration will be also more, which we will see here. If you see this diagram, so whenever this deceleration is happening, so you are able to see here, these are the motor current, which is coming in the positive part. So positive part, what I have told, is a regeneration part, and negative part, what I have told, this is a hello, am I audible? Because in between I have to check my internet connection also.
No, sir, you are audible, sir.
Okay. Okay, so thermal heat load estimation we are seeing here. So one heat load is coming from the battery pack and one is coming from the electric powertrain, which is one from DC-DC converter and the TC, which is nothing but your motor inverter. So as your motor current is changing, either for positive current or negative current. So here in this case, motor current. So whenever there is a positive current, means you are accelerating here. Okay, and negative means you are decelerating here. You are recuperating energy from the brake force. So motor change is happening. So based on the motor change, you will have heat rejection. So you will always provided by the map, like for the inverter with the current interaction, you will be having the heat load unit. So this kind of map will be given for these two gentlemen for DC-DC converter. It will be like heat rejection versus current drawn. Okay. Here current drawn is positive, negative. It's only for sign convention. It is always considered that either whether current is negative also, heat rejection will happen. But it's only changing the sign, because acceleration, because energy consumption and recuperation is there. That is the only thing. Okay. So don't confuse with the positive and negative sign. So for this also you have positive heat rejection, and for this point also you have positive heat rejection. So that's the reason when I convert this graph into this formula, so we will get this. If you see this one also, for negative also, I have the positive heat rejection value here. Okay, so this will directly imposed on the your thermal management equations or thermal management architecture which we have considered. The same thing is coming for the battery pack also. So in battery pack, since motor current is only providing for charging for the battery system, so during acceleration or during deceleration, uh, there will be always positive uh, uh, heat rejection will be there in the battery pack. So all will come in the positive, and all you have to consider during thermal simulation, thermal load estimation. I hope this point is clear. Uh, Now, I have discussed this like empirical correlation. So based on the empirical correlation, we are modeling. So here I have modeled with commercial software, MSIM, but you can the same methodology applied for your MATLAB also or any other open forum software. So what we are doing here, we are providing this heat load. So these are the heat load, okay, which is nothing coming from the this this estimation, this rough estimation, and all the components will have mass. Okay, so this OBC has mass, this DCDC has mass, this traction control unit has mass, and there we are providing this liquid cooling system. Okay, so now here interact here what is happening here, convection heat transfer is happening, and this is nothing but a pipe flow. So there you are using actually using the correlations, or or you can say in other word the the correlations developed by the test measurements which we have told, like you are doing this steady state flow, or you are doing your transient dynamic flow. There you are using it, and the same low temperature radiator will come, and one auxiliary system, nothing but your water pump will come, and you will impose the airflow which is supplied through the help of your electric fan. So based on that one, you will be able to simulate the temperature. Here, since I am using the commercial software, so I have the visualization much easier. The same thing you can plot in MATLAB also. So all things, I think SimScape, everything is there. So based on that one, you are able to see the temperature of the sync temperature of the TCU, DCDC, and OBC. So only thing what is here, what is happening here, we are able to see the temperature, but as a lumped analysis. We are here we are not doing any contour, temperature contour. Okay, so let's suppose if you have this complete DC-DC area, this is let's suppose 10 centimeter, 10 centimeter. So complete mass we are telling this is the temperature. So that is the only limitation when we are going with 1D simulation. But when we are coupling with 3D versus 1D, then this contour will also you will get it. So the contour will just look like this one. So there you have hot spots, like where heats are more, it will be highlighted in more red, and this will be something blue. Okay. Now this is the complete powertrain architecture modeling. So where we have this electric powertrain, cabin cooling, and battery cooling circuit. And if you are able to see here, so this is the model which I have discussed earlier, in which you have certain drive cycle, and this battery will be providing this traction load requirement. But here we have considered other things also. Auxiliary system. Auxiliary system is nothing but your battery cooling system, cabin cooling system, as well as your electric powertrain cooling system. Okay. So electric power cooling system, what I have done here, I have done that separately, and whatever the power consumption requirement is coming, I have directly added here for this electric system, electric powertrain system. Now, for this cabin cooling, I am deploying heater. I am deploying your compressor. This is a high voltage system. So the battery is directly providing this to your compressor, and this compressor is again routed in two forms. One is for evaporator, and another will for the chiller. This is the same architecture which we have seen, that same circuit will be T-joint. One is into the chiller part, and one is into the evaporator part. So exactly what we are doing here, we are considering the thermal mass of the vehicle, and the way we have estimated the load from the internal resistance. So that we are directly imposing here at this location. So from this heat is directly imposing here, and this is the battery mass. I will just make it So based upon the traction requirement and energy requirement for this cooling, so temperature of the battery will change. So based on the temperature requirement, here it is connected as a heat to the battery mass. Now battery mass will tend to increase. Battery mass is nothing but your battery cell, which is tend to increase the temperature. And our aim is to keep it 15 to 35 degrees Celsius. So that is the reason here your liquid cooling channel has been deployed. Okay, and it is supported with the chiller unit. So based upon the requirement, whenever I am getting triggered, like temperature has shooted more than 35 degrees Celsius, so the chiller will be triggered off and triggered on. And when it is coming to below 15 degree or maybe below 30 degree, again it will be triggered. This chiller will be switched off. Now, when we are operating in 0 to 15 degree, the same coolant loop will be deployed here to heat the battery pack. Okay, and now when we are dealing with minus 30 to 0 degrees Celsius, then instead of chiller, we will be using here heater separately. Okay, so this is the detailed modeling. So this consists of your battery cooling, electric powertrain cooling, and what will be the outcome of this modeling? So this outcome of the modeling will be, we will be able to know the flow of energy from battery to grid. This model looks little complicated in 1D simulation because I'm using the commercial software, but it is very easy. You have to follow step by step, and you can able to replicate this thing in Excel. I can say Excel as well as your MATLAB. Okay, so once you are achieving this kind of modeling, you will be able to know the energy interaction from the battery to wheel and from wheel to battery. You will be able to know the vehicle range. So you are able to front load your vehicle virtually. That if you are designing a 40 kilowatt electric powertrain, so what vehicle is going to give the range in different ambient scenario. Third thing, thermal load estimation you are doing. So component life cycle you are able to see it by doing this kind of analysis. Third thing, auxiliary power consumption. So auxiliary power consumption we will also know. So since we know we have to make the ideal system. Ideal system means auxiliary power should be minimum and all power should go to the traction requirement. So once you are developing the model, once you are developing the calculation, you will come to know exactly, okay, 50% is going to the auxiliary system. Can we do something? Then your architecture will come into picture. Okay, what are the different architecture we have available to include my modeling or to include my analysis, so that the auxiliary system power will come down. Second thing, once you are integrating everything, so and you have a different range of temperatures to meet desired value. So from 15 to 30 degree up to 65 degree for powertrain, for motor 85 degree, and your operating point is minus 30 to 50 degree. So you will be able to develop the thermal control logic. So the question which we have asked, whether the same system is capable to deliver the board or whom should prioritize. So that kind of question you will be able to answer from this. So these all from my side in thermal management. So I'm open for our Q&A. So any doubt you have, you can ask me.
Yes, sir. Sure, sir. And thank you for the session, sir. It was really informative for us. And there is one question in the chat box. I'll just convey it to you, sir. In case of a battery got fire, then how we can control the fire, as battery has chemicals?
So this battery fire is basically a safety requirement in the thermal modeling. So what is happening for the battery fire?
Yes, sir.
So there are sensors placed on the battery system. So when it is sensing that a very high abnormal behavior has changed in the battery in terms of temperature, because battery pack is covered with full of temperature sensors as well as current continuously monitoring happening. So once the sensor has detected that temperature has gone up or your current has gone up, so what it will be do? It will discharge the battery from, let's suppose your battery has 100% charge. Okay, and at that case some accident has happened. in this case, it will discharge the battery within 15 seconds to avoid the further any battery fire application. Fire. Because if the battery power is not there, then fire will not proceed further. So this we consider as a safety requirement, and this will give as an inbuilt parameter to the battery pack.
Okay, sir. So if there are few more any questions from the participants, they are free to ask in the chat box. Okay, sir. Those are the few questions in the chat box, sir. With your permission, shall I conclude the session, sir? There is one more question. Can I just convey to you, sir? What are the softwares used?
See, for my application, I have used the 1D simulation software that is called AmiSim. It is from Siemens. But don't go in the software part, methodology, because this is the same software. You can say this is the same software in a user is a must user definite user means I can say it's like a MATLAB software only. Only thing in MATLAB you have to do certain kind of coding. This coding is not required.
Okay, sir. I think there were the few questions from the participants, sir. Shall we conclude the session, sir, then?
Sir, one question, sir.
Yeah, Mahindra.
Sir, have you included in your this model from this whatever the heat generated by the cable or some other devices, like as a wires?
No, we have not considered the cables thermal because if we consider the battery pack, the design is such way that the cable should not hit. Otherwise, what will happen? We will lose energy by delivering the power from one module to another module. So that those heat loss are very minimal, and we are not considering in thermal management.
Okay. Thank you, sir.
There is one more question from Dr. Kripa, sir. Any other softwares we can use for this?
I know some commercial software. One is your GT Suite. Second one, your COMSOL multi-physics, you can use it. AmiSim, you can use it. Flowtherm, you can use it. Cooling, you can use it. But it is very well, you can use your MATLAB.
So if there are any few questions that has to be conveyed to the speaker, they can free to ask, or they are allowed to put it in the chat box. Either of the ways accepted. Please share them.
And if the participants are getting questions, maybe after this session also, so they can email me, I will answer those things.
Sure, sir. Okay. So
I hope this session
there
was
are no more
interesting.
questions, sir. Very much, sir. Okay. Shall I conclude the session, sir, with your permission? Okay. Thank you, Ravi Ranjan, sir, for the beautiful session, and it was really informative for us, and it has enlightened us on various aspects of thermal management or battery thermal management. It was very informative for us, and we also like to thank you on behalf of all the participants and from the organizing committee of Bangalore Institute of Technology and Engineering for the beautiful and wonderful session, sir. Thank you, everyone, so much.
Thank you. Thanks a lot.
And
thanks to Rav Sethur, sir,
yes,
to providing this opportunity to deliver a session.
Okay, sir.
So,
So that ends the session.
yeah.
That ends the session for this particular topic.
Mr.
And
Madhusudan,
there's one more session.
one more thing. Here is
Yeah.
an information to all my participants. Dear participants, kindly bear with us. Today, one more session is there. That is in the evening, 7 to 8:30. A professor from Binghamton University will be delivering. He will be delivering a talk on autonomous navigation system. It is very wonderful session. Um, During that time, for him, it is will be early morning. So we cannot arrange in the evening in the day session here because from New York and here, almost about 10 hours or 12 hours difference. That's why we are arranged one session today at 7 p.m. Kindly join that well in advance. By 6:45 itself, please join for the session. Thank you.
Thank you, sir, for that information. And even I request for the same. So session 7 will exactly start at 7 p.m. You can join with another link, which is shared to you by now. So that concludes the session for this particular day. And one more session, which is session number 7 by Dr. Yang Wong, will begin at 7 p.m. in the evening. So you're requested to join the same. Thank you, one and all. Have a great time ahead.
Many people. Stop on.